Well, good morning, everyone. Today we're going to be talking about the last section here in chapter 12.1. This is going to be on the hypothesis test for a slope of a regression line. So I think we all kind of know what that means by now. So let's take a look at our work. So Mr. Ferreria is wondering if there is a relationship between GPA and ACT score. He took a random sample of 9 of his 101 students and recorded their GPA and ACT scores. The data are below. So here's our random sample of 9 students out of 101. And the first question here is, what kind of relationship would you expect the GPA and ACT scores to have? So remember, this is a statistical relationship. So we have to try to use some of the vocabulary that is appropriate here for statistics. An appropriate response here would be something like, I would expect a positive relationship. As GPA increases, I would expect the ACT to increase as well. So remember, positive relationship here, that's purely a mathematical construct. Positive relationship means both quantities increase together. Okay, so here's a mini tab output as well as the graphs of the data. Here's our output, and we're going to do a little bit of a review here. This right over here is our value of B. Here's our value of S. Right over here, this is our value for SEB. And then right up here, this is our value for A. Okay, let's take a tour of the data. This seems to be a positive relationship. This graph here doesn't actually have any markings on it or any axis clarification, so we don't actually know what either of these are. But judging by the scale down here, 1.5 to 4, this is probably GPA. And since this goes up to 36, this is most likely the ACT score on the vertical axis. Residual plot, I don't see a pattern. I don't see a curve in it, and I don't see the sideways triangle or the Christmas tree here. So I think this is okay. Residual plot, -6 seems like it's low, but in relation to the rest of them, no, not really. So there is no strong skew and no outliers in the residual plot. So our first task here is to find the LSRL of the data. And luckily for us, we already highlighted the values of A and B, or I guess as we're calling them now, B0 and B1. Here again, I'm going to advocate that you write these as predicted ACT score and GPA instead of using the Y hat and X notation that a lot of people seem to favor. This will build or bake your context right into your equation, so there's no confusion about what any of this means, and you don't have to worry about defining what is Y and what is X. Number 3. Do the data provide statistical evidence that there is a positive linear relationship between GPA and ACT? And I'm going to remind you again of this language here. This phrase, do the data provide significant evidence or significant statistical evidence, that is a buzzword to tell you to use the 4-step plan. So now that we know that we are going to do the 4-step plan, let's take a look at the 4 parts. And the first one is state, what is our parameter? Our parameter here is beta1, and beta1 is the slope of the population LSRL between GPA and ACT score. Here we have our statistic is B1, which is 7.507. Now I want to take a pause here and kind of remind you about what we're doing, because as I wrote that 7.507, I thought, well, that's clearly a positive number, so obviously there's a positive linear relationship. And remember that that's not really the point. Yes, that is a positive slope, but is it positive enough that it is not affected by sampling variability? In other words, is the relationship between this statistic and the sampling variable such that even with sampling variability, the slope of the regression line would still be positive? So that's really what we're trying to figure out here. The fact that we have a positive 7.5 for the slope means that we could probably tolerate a little bit more sampling variability, but not too much sampling variability, obviously. Okay, so remember, if you answer the question and you don't use or you don't talk about sampling variability, then you're not really using statistics. You're just using, middle school mathematical concepts to answer a more complex question. And that's not what we're doing here in AP Statistics. Next, we have our hypotheses. Beta 1 is equal to 0 versus beta 1 is greater than 0. And I want to remind you again over here that we're asking if it has a positive linear relationship. And that's why we're testing to see if beta 1 is actually greater than 0. No alpha was given to us in our question, so we're just going to presume our alpha level to be 0.05 or 5%. This is a one sample t-test for beta 1. And nicely here, they've gone ahead and given us all 5 parts of liner, so we don't have to, or that'll help us remember it in the future, so we can have this memorized. Linear, that scatter plot revealed a linear pattern, and there was no leftover curve in the residual plot. We'll refer to you up over here again. Linear pattern in the scatter plot, residual plot, no curve. Next, independent. 9 has to be less than 10% of all of FERRERIA students, which is true because FERRERIA has more than 90 students. Now, I want to remind you that we actually were looking at a random sample. So because we're looking at a random sample and not looking at a random assignment of treatments, we are obligated to qualify that 10% condition. 10% condition doesn't need to be met if you're doing an experiment. It does need to be met if you are doing an observational study. Normal. For normal, we're looking at the dot plot of the residuals, and our dot plot of the residuals showed no strong skew nor any outliers. For equal standard deviation, we're looking at the residual plot. And again, the residual plot does not show a triangular pattern. Taking a look here, this is not a triangular pattern. Well, maybe you might argue that there is a little bit of a triangular pattern, but it's not enough to worry us too much here. And lastly, random. Up over here in our question, we took a random sample of 9 of his 101 students. We'll quote that and put it into our list of conditions, and we have done it. We have qualified on all 5 of the liner conditions. The scatter plot was linear. We have less than 10% of all of the population. The dot plot of the residuals did not show strong skew or outliers. The residual plot did not show a triangular pattern, and the sample was a random sample. Let's move on to the do part, where we have the general formula. For a hypothesis test, your general formula is always test stat equals stat minus null over standard deviation. For the one sample t-test for beta 1, the specific formula, specifically for this, we have test stat equals B1 minus beta 1 over SEB. So let's take a look back at our chart and let's try to find all of those quantities again. Over here in yellow, that's B. In green over here, we have SEB. And if we look at our hypotheses, we're going to get beta 1. Beta 1 is equal to 0. So when we get to our work, we're going to get 7.0507 minus 0 over 1.29. Again, remember the 0 comes from the null hypothesis. This gives us a test stat of 5.819. While we're at it, let's also remember that the degree of freedom is going to be 9 minus 2, which is, of course, 7. A picture of the t-curve. Well, we just draw a normal curve, but it's not really a normal curve, so we're going to cross that out. And instead, we're going to label that a T7 curve. Now, a test statistic of 5, positive 5 here, that's going to be way out over here on our curve. And there's going to be practically 0 area there. So that kind of gives you an indication about what our p-value is going to be. Finally, we're going to compute our p-value using our TI calculator. We're going to get to our distribution menu. Then we're going to click over to TCDF, which is number 6. Our lower is going to be our test statistic, since we are looking for greater, as our alternative hypothesis says. We got a test statistic of 5.819. We're going to go to positive infinity, so we're going to write the biggest number on our calculator, which is 1e99. And our degree of freedom, that's going to be 9 minus 2. I always just like writing 9 minus 2 and not bothering with 7, just because it kind of reinforces how to get that degree of freedom. All right, we're going to hit enter, and we have 0.0003. Remember that if you're reading this on your calculator and you see this e to the negative 4 here on the far right here, that's scientific notation. So this is technically 3.25 times 10 to the negative 4, or 0.00325. We're going to write that down in our work. And then we're ready to go with our conclusion. Modifying this for the situation, we have a p-value that is less than alpha. So the data is going to support the alternative hypothesis. Since the p-value is less than alpha, 0.03% is less than 5%, the data supports that. Okay, so what's our alternative hypothesis? It is beta greater than 0. So it supports that beta 1 is greater than 0. But what is beta 1? We got to put this in context, remember. Beta 1 is the slope of the population LSRL between GPA and ACT score. Last thing we're going to write here is going to be the convincing evidence part. So we have convincing statistical evidence of a positive linear relationship between GPA and ACT score. Note-wise, I want to remind you that generally speaking, if your p-value is less than alpha, you have convincing statistical evidence for whatever you're trying to prove. And if your p-value is greater than alpha, that means you do not have convincing statistical evidence for whatever it is you want to prove. And this brings us over to our important ideas. Now, at this point, we've probably done dozens of hypothesis tests. So we're just going to talk about the parts that are really different here. And the first part that's different is the hypotheses themselves. So in our hypotheses, we've got beta 1 equals 0 versus beta 1 is not equal to or greater than or less than 0. Typically speaking, in AP statistics, we're going to be using 0 for our null value. Now, the conditions and formulas that we have here, well, the name of the test is always going to be the one sample t-test for beta 1. The conditions are linear, and you should really look at the previous video if you want to see those notes for what linear stands for. It's a lot more than what we can write here. And then, of course, our test statistic is going to be equal to B1 from the chart minus beta 1, which is from the null hypothesis, divided by SEB, which is from the chart. Degree of freedom, n minus 2. Okay, let's check our understanding here. We've got infants who cry more easily, may be more easily stimulated than others. This may be a sign of higher IQ. Ooh, infants who cry more easily may have higher IQ. Interesting. Child development researchers explored the relationship between crying infants 4 to 10 days old and their later IQ scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying of 38 infants. They measured the crying intensity by the number of peaks in the most active 20 seconds, and they later measured the child's IQ 3 years, at age 3 years, using the Stanford-Binet IQ test. Here is a computer output for the least squares regression analysis of these data. Do these data provide convincing evidence at the alpha equals 0.05 level of a positive linear relationship between count of crying peaks and IQ in the population of infants? Assume the conditions have been met. Now, as far as these tests are concerned, a lot of times you're going to see that phrase, assume the conditions have been met. When you see that, don't even start with the conditions. Just move on. It's very important. Those are put there for you for some very important reasons, not the least of which is it's going to save you a little bit of time. So let's take a look at our chart. We only really need 2 numbers from here. We need the value of B, and we also need the value of SEB. And we'll go ahead and get started with state. We've got beta 1 is the true slope of the population LSRL between cry count and IQ. We've got our null hypothesis, beta 1 equals 0, versus the alternative, beta 1 is greater than 0. Remember that we're using greater than 0 because our question told us to use a positive linear relationship, or to test to see if there is a positive linear relationship. And our significance level is 0.05. In the plan section, the name of our test is a one sample t-test for beta 1. And for the conditions, we're just going to quote from the problem where it said, assume conditions have been met. It's sometimes baffling to me that I have to remind people how to correctly use quotations, but I guess that's the way we do it. We're moving on to the do section. Our do, we have our general formula is test stat equals null minus hypotenuse over standard deviation. The specific formula here is the test stat is going to equal 1.4929 from the chart minus 0 from null hypothesis divided by 0.4870, which is from the chart again. And I just realized something. Yeah, I wrote down the work instead of the specific formula. My mistake. So what do we have here? We have the specific formula is test stat equals B1 minus beta 1 over SEB. The work we already showed. This means our test statistic equals 3.07. We're going to draw the picture of our normal curve. Well, this isn't a normal curve actually. This is a T36 curve because our degree of freedom is 38 minus 2. Notice that we have highlighted, or we have the red region is the p-value, and it is at 3.066. It is shading to the right because our alternative hypothesis, if you will remember, was beta 1 is greater than 0. Okay, p-value time. Our p-value here is the probability or the proportion on the t-curve that's greater than 3.066. And using our TI calculator, we get 0.002, which inevitably leads us to our conclusion. Since that p-value is less than alpha, 0.2% is less than 5%, the data supports that the true slope of the population LSRL between cry count and IQ is positive. The data provides convincing statistical evidence of a positive linear relationship between cry count, count of crying peaks, and IQ. So that does it today for our AP Statistics, and hopefully you'll find that these hypotheses tests for the slope of a regression line, they seem like they're a big deal, but they're really not. Most of the data is kind of laid out there for you. And I'm sure you'll find that more times than not, you're going to have to assume that the conditions have been met. So anyways, that's it for me. Have a good day and happy statting.